Hello, in this presentation I will be talking about robophysical and simulation modeling of how leg posture affects vibration sensing in orb-weaving spiders. Orb-weaving spiders are blind to their surroundings. They can operate in complete darkness yet are extremely apt at navigating and identifying stimuli on their webs. The reason is that spiders sense vibrations on their web. For example, if you hold a tuning fork on a spider web, the spider will react to its vibration. So, in this presentation, we will try to understand how they can sense and understand these vibrations. We will be focusing on the orb-weaving spiders that produce spiral circular shaped webs. Research on spider anatomy has shown that spiders sense vibrations via lyriform organs, a group of slit-like organs that detect strain. There are nerve endings in these slits and activate when the lyriform organs are compressed. These lyriform organs are extremely small and thus are very sensitive to vibration. Lyriform organs are located all over the spider legs, as seen here. Certain lyriform organs are particularly important and sensitive to vibrations, such as the HS10 lyriform organ here. While this is research based off of ground hunting spiders, it is generally applicable to orb-weaving spiders too. So, for orb-weaving spiders, they sense the result of the vibrating stimulus that starts from the source of the web, through the web, to the feet, then towards their lyriform organs located in each of their joints. The vibration has to pass through each joint, and thus each joint senses a different vibration. The joint vibrations will compress the lyriform organs in an oscillatory way. This means that the spider has to interpret and understand the vibrations in its joints to understand information about the vibrating stimulus. What's important here is to understand that spiders do not sense the web vibrations directly. Previous studies have tried to understand how vibrations propagate through the web for spiders to sense. These studies include studying the overall vibrational properties of a web, studying the types of waves in the web and the information they provide, studying how web properties affect these waves, and studying how web vibrations can be used to locate stimuli. These studies only quantify web behavior, not the spider body. Most of these studies do not have an active spider, and for the studies that do, they only qualitatively measure the spider's response. To understand more about spiders, the Gordas lab that my lab collaborates with has a setup to observe spider behaviors. Through these videos that they have collected, they can identify closely many behaviors that the spider does on the web. Here is a video of a spider constructing its web. The spider we investigate in this presentation is the Lulaboris diversus, which likes to hang upside down on its web, as you will see in many pictures in this presentation. In one of the recordings, we can see that the spider is reacting to a fly landing on its web. What is interesting here is that the spider changes its posture, seemingly to identify the source of the vibration. You can see here that in addition to changing its posture, the spider is pulling on the web and increasing tension to the spider web. This will change the vibration. This leads to the hypothesis that spiders actively adjust leg posture to filter web vibrations that help them sense prey and mates. This is unlike usual morphologies that use passive mechanics to filter out stimuli for sensing. One study supports this hypothesis, seeing that black widows change their posture depending on their state. The authors of this study identified how black widows have a neutral state, like to bend forward when in the courting state, or in the hungry state, they like to crouch. Uh, Note here that the black widow is not an orb-weaving spider, but a cobweb-weaving spider. So in order to do this experiment, they vibrated the tips of each type of spider leg and measured the vibration profile for each leg joint. The plot here shown is the vibration profile for one joint of the leg. This is done through applying the fast Fourier transform of the resulting leg joint vibration response. The different vibration profiles of the leg indicate here that these different postures that the black widow assumes changes the vibrational profile of the spider. This leads to an assumption that posture changes allow the black widow to tune into certain frequencies. However, since vibrations are difficult to measure on a biological spider body, this theory was only tested in a simulation with no web involved, not in a real system. There is still no study on measuring the vibrational response of an active spider body on the web. Doing experiments with an active spider body is particularly difficult since there are many different factors involved that change and need to be measured on the spider when it is actively sensing on its web. This includes the inertia distribution, Web tension changes due to pulling when in those postures, and stiffness changes due to muscle activations to be in a certain posture. All these factors are difficult to measure on a small moving spider body. Thus, we use a robophysical model and a physics simulation to verify our hypothesis that spiders use active sensing to understand vibrations in their webs. This is a very early stage research project, so we will be only talking about number one, the inertial distribution. We will be investigating this without the web. We plan on doing 2 and 3 in future investigations. To begin with our robophysical model, we first have to create a simple spider model to understand the dynamics of a posture change. A spider leg contains many joints, but we simplify it to only having 2 joints for our robophysical model. Each joint has an accelerometer to measure the vibrations just like the lyriform organs would, sensing the joint angle vibration, and a torsional spring to replicate joint stiffness. We then connect these joint segments together to form a leg. To adjust the leg posture of the spider model, we would just change the resting angles so that our robophysical model can assume various postures. We then connect these legs to a central body, connecting each leg to a ball and socket joint connection to mimic the attachment a spider has on its web. We test the robophysical model in 3 different postures: a crouch posture, neutral posture, and a hanging posture by changing the leg angles into various positions. To test the robophysical model, we use a motor and a rod to hit a rubber connection one of the spider joints is attached to. You can also see a demonstration in this video. For the experimental trials, we collect 5 trials for each posture, clip out each trial, and convert each waveform response into a vibration profile using the fast Fourier transform. We then combine these results to form an aggregated plot with error margins for each posture. The low error margin here also shows that the robophysical model is consistent in its vibration response. From the experimental results, we can see that the posture affects the vibration response depending on what the posture the spider is in. You can see the magnitudes and the peak frequencies that the robot senses is different depending on what posture it is in. This supports the idea that posture does change vibrational response profiles as seen in the Black Widow study. We also accompany this model with a simulation. Using the physics simulation model helps so that we can quickly vary parameters, increase the amount of data we acquire from the experiment, and gather insights that the robophysical model by itself cannot lead to. To make the simulation, we use Project Chrono, a multi-body dynamics physics-based modeling and simulation software. To make the joints, we apply a torque equation that is dependent on the angle state of the 2 bodies that the joint is pointed to. Again, the simulation is also perturbed by an impact on the oscillating rubber in which the vibrational response of the joints is recorded. The simulation is also divided into the crouch, neutral, and hanging posture. You can see that the peaks are in different locations for each posture's vibration profile here too. However, as you can see here, the experiment and simulation vibration profiles do not match. There are many reasons for the mismatch between our models and simulation. The shapes of the models do not match despite having similar parameters. The friction is too high in the joints, causing unideal spring behavior. And there is a mismatch in the locational attachments. So, we updated the robophysical model. We made an 8-legged version of the robot with improvements to address these issues. So in the beginning, there were 3 things that we mentioned that were important to measure for active spiders. In this presentation, we have shown 1, that there is a postural effect via change of inertia distribution. For our future work, we need to compare our new simulation results for number 1. In addition, we need to add a spider web to both the simulation and model and measure the effects of posture there to address 2. We already have our model webs built for each system and plan to attach our spider on there. We also need to change joint stiffness to address 3. We have changed our new spider model to allow for easily replaceable springs so we can try different joint stiffnesses. Finally, we also need to add actuation so that the model can actively change the angles of the spider joint during sensing, just like a real spider changes its posture to identify sources of vibration. This can also include a vibrating prey model. Here are the people I would like to thank for this presentation, and thank you.